So okay, so first of all, let's discuss what we have. So first of all, we have a histogram, right? So that's kind of what we plotted. And again, the histogram can be plotted in different granularities. The default is we divide the space into 10 bins and plot how many samples are there in each bin. Of course, we can divide it into 100 bins, and that gives us a finer division, but then a little bit more noisy. If we divide it into 1,000 bins, we would have even a finer division, but then we can already see the integerness of this of the samples, right? So because the number of samples in each bin is an integer, right? So and of course it's becoming more and more noisy. And imagine we have more and more samples. The noisiness of this CDF is going to get smeared out. And what we had is, let's say this is the wind speed, and this is the we call the probability density function.
We can say wind speed for PDF.
Or so-called PDF. So what does it mean? It's equivalent to a histogram with infinitely many samples. But the problem is that a histogram is a count of how many samples is within each bin, right? Here we have 20 count or 21 count or 22 count. It's discrete. And imagine we have 10 times as many samples. Probably we'll have about 10 times as many samples in each bin on average. So with infinitely many samples, the histogram is going to be infinity almost for every bin, right? So then what does it mean by a histogram with an equivalent of infinitely many samples? Well, actually it's easy, because every time we increase the number of samples by a factor of 10, the height of the histogram grows by a factor of 10, right? So why don't we normalize the height of the histogram by the total number of samples we have? So that's one thing. That's one thing we can do. Is the histogram, why don't I disappear? Histogram normalized by, let's see, 1 is the number of samples. All right. Now there is another problem. Remember, after we divide it by 1,000 samples, we see the numbers are on the range of 20 to 40, and we see the discreteness of the number of samples. But back when we had 100, the numbers are actually so high that we didn't really see the discreteness. So the height of the histogram doesn't only depend on how many samples there are, it also depends on what?
The bin size. The
bin size, right? So the histogram also has to be, in order for us to actually go to not only infinitely many samples, but also infinitely many bins, we have to also normalize by the width of the bins. So basically, from a histogram, which is a discrete or finite sample version of how the distribution look like, to the infinite version, we have to normalize with respect to two things. One is the number of samples, and two is the width of each bin, right? So okay, width of bin. All right. Okay, so basically, if we do that, it becomes easy, because the number of samples in each bin, of course, is proportional roughly to the number of total samples, and is also proportional to the width of each bin. So the PDF of a distribution at x is basically equal to the number of samples within an interval x minus delta x and x plus delta x divided by the total number of samples. And what? The bin size, in which case is 2 delta x, right? So there is a more mathematical definition, but empirically speaking, this is what the probability density function look like, right? It's basically the density of the samples when you have infinitely many samples and a tiny size. And basically, this is really defined as the limit. So let me remove this. Is equal to the limit of delta x goes to 0 and the number of samples goes to infinity, right? So that's the proper definition of the PDF.
So